Hello, in this lecture we will find the radius of the small circle. In the drawing we have two circles with internal lunge between them at this point. Let's define this point as point N. Point N is the point of contact between the two circles. That is to say, those two circles are touching each other at point N. Point N is the point of contact between those two circles, and it's actually called internal lunge. Okay. In addition, we have line segment AC that equals to 9 units. We have line segment PD that equals to 4 units. This is a right angle. This is also a right angle. And we have also 3 tangents to the small circle. 1, 2, and 3. Those are tangents to the circle. Actually, this line segment is a tangent to the circle at this point. Let's call the point of contact between the line segment and the circle point S. Okay, point S is the point of contact between the line segment to the circle, or actually this line segment is tangent to the circle at point S. Then we have the second tangent to the circle at this point. Let's call this point Z. Again, point Z is the point that this line segment is tangent to the circle, or the point of contact between the line segment and the circle. And we also have a third tangent to the circle. Line segment CD is tangent to the circle at this point. Let's call the point of contact between the line segment and the circle point M. And we also know that chord AB is the diameter of the big circle. Again, chord AB is the diameter of the big circle. Okay, so first of all, let's define the center of the small circle as point Q, and we define the center of the big circle as point P, and let's define the radius of the small circle as small r. Small r is the radius of the small circle, And let's define capital R as the radius of the big circle. Capital R is the radius of the big circle. Okay? Small r is the radius of the small circle and capital R is the radius of the big circle. Okay? In the next step, we will draw 3 radiuses of the small circle from the center of the circle, that is to say from point Q to the point of contact of the tangents to the circle. So here we will draw the radius of the small circle from point Q, that is the center of the small circle, to point S, that is the point of contact, or the point this line segment is tangent to the circle. Okay, so SQ is the radius of the small circle, and it starts from the center of the small circle, that is to say from point Q, and ends at point S, that is the point of contact of this line segment with the circle, or the line segment, this line segment is tangent to the circle at point S. So actually we have a rule that the radius is perpendicular to its tangent. Because of the fact that this line segment is tangent to the circle, then the radius is perpendicular to its tangent. For that reason, this angle is a right angle, it equals to 90 degrees. And we also know that this angle is a right angle, and we will draw the second radius of the small circle from point Q to point M. That is actually the point of contact of line segment CD with the circle, or line segment CD is tangent to the circle at point M. So because of the fact that the radius is perpendicular to its tangent CD, so this angle is 90 degrees. This angle is also equals to 90 degrees because of the fact that the radius is perpendicular to its tangent CD. Okay, then we'll draw the third radius of the small circle from the center of the circle to point Z, that is the point of contact between the line segment to the circle. So actually the radius is perpendicular to its tangent, and actually this line segment is tangent to the circle at point Z, and the radius is perpendicular to the tangent. For that reason, this angle is a right angle. So we actually we have here a square. QZMD is a square with 3 right angles. Okay, so QZ shape QZMD, this shape is a square with 3 right angles. This is a right angle, this is a right angle, and this is a right angle. So shape QZMD has 3 right angles. It is actually a square with 3 right angles. And we have a rule that states that the sum of the angles in a square equals to 360 degrees. The sum of the angles in a square equals to 360 degrees. Okay, the sum of the angles in a square equals to 360 degrees. So here we have a square. QZMD is a square with 3 right angles. So the sum of the 3 angles equals to 90 times 3 is 270 degrees. So actually the 4th angle must complete the total sum of the angles in the square to 360 degrees. So the 3rd angle must be equal to 360 degrees minus 270 degrees. Okay, 360 degrees minus 270 degrees is the value of this angle. 360 degrees minus 270 degrees equals to 90 degrees. That is to say, the 4th angle is a right angle. And any square that has 3 right angles is a rectangle. Therefore, QZMD is a rectangle. Okay, QZMD is a rectangle, and in any rectangle the opposite sides are equal to each other. So QZ equals to MD. And we know that QZ is the radius of the small circle, and QZ equals to MD. So MD also must be equal to the radius of the circle. Because of the fact that the opposite sides in any rectangle are equal to each other, if QZ equals to R, then MD that is opposite to QZ also equal to R. Okay? And we will repeat on the same process on the shape SQCM. Okay, in shape SQCM, shape SQCM is a square and it has three right angles. This is a right angle, this is a right angle, this is also a right angle. So shape SQCM is a square and has three right angles, and the sum of those three right angles is 90 times 3 is 270 degrees. Okay, and the sum of those three angles equal to 270 degrees. Therefore, because of the fact that the sum of the angles in any square equals to 360 degrees, the fourth angle must be equal to 360 degrees minus 270 degrees. Okay, that is the value of the fourth angle, and 360 degrees minus 270 degrees equals to 90 degrees. Okay, that is the value of the fourth angle. So the fourth angle is also a right angle. This is a right angle. So we actually have a square with four right angles. And any square with four right angles is a rectangle. So SQCM is a rectangle. Shape SQCM is a rectangle. That is to say, the opposite sides of any rectangle are equal to each other, so SQ equals to CM. Therefore, SQ equals to CM. The opposite sides in any rectangle are equal to each other. SQ equals to CM. But we know that SQ equals to R, so CM also will be equal to the radius of the small circle. Okay, so CM equals to the radius of the small circle. Okay, in the next step we will define PM as x, that is to say PM equals to x. Okay, PM equals to x according to our definition. Okay, PM equals to x. So the value of Cp will be equal to Cm minus Pm. Again, the value of Cp will be equal to Cm minus Pm. That is to say, the value of Cp will be equal to Cm, that is R, minus Pm, that is X. Or Cp equals to small r minus x. Okay, again I write it down that Cp equals to small r minus x. Okay, and in the next step, actually we know that the center of the big circle is at point P, so actually AP is the radius of the big circle, that is to say AP equals to capital R. Okay, AP equals to capital R. That will be our first equation. AP equals to capital R. And what is the radius of the big circle? R, the radius capital R, the radius of the big circle, equals to AC plus CP. Again, the radius of the big circle, that is actually AP, equals to AC plus CP. Okay, so you can write down that the radius of the big circle equals to AC plus CP. AC plus CP. Okay, the radius of the big circle equals to AC plus CP. But we know that AC equals to 9 units and CP equals to 1 minus X. So actually the radius, according to equation number 1, the radius of the big circle, that is to say capital R, equals to AC, that is 9 units, plus CP, that is R minus X. Okay, so we got the equation for the radius of the big circle. It is equals to 9 plus small r minus x. Okay, that is the radius of the big circle. But we have another way to calculate the radius of the big circle, because the radius of the big circle is actually equals to PB. PB is also the radius of the big circle, so capital R equals to PB. So second equation is states that capital R equals to PB, that is the radius of the big circle. And what is the value of PB? The value of PB, that is actually capital R, the radius of the big circle, equals PB equals to BD plus MD plus MP. Okay, PB equals to BD plus MD plus MP. Okay, so the radius of the big circle equals to PB, and PB equals to BD plus MD plus MP. Okay, so BD is actually 4 units. It is given us in the question. BD equals to 4 units. MD equals to the radius of the small circle. MD is small r. And MP equals to x. According to our definition, MP equals to x. So actually, when we calculated the radius of the big circle in the second way, it equals to 4 plus r plus small r plus x. Then you can create the further equation that states that capital R equals to capital R. Capital R, as we calculated it in equation number 1, equals to capital R as we calculated it in equation number 2. Okay, so that will be our further question that states that capital R equals to capital R. Here we'll substitute this R by further equation, by the first equation, and we'll substitute this R by the second equation. Okay? And we will get that capital R in the first equation is actually capital R, according to the first equation, equals to 4 plus small r plus x. And all equals to capital R as we calculated it in the second equation. And capital R in the second equation is actually 4 plus small r plus x. Okay, so that is r equals to r. Here we put the value of r according to our first equation, and here we put the value of capital R according to the second equation. Okay, we have small r in this side of the equation, and we have small r in the other side of the equation, so r is cancelled, and what is left after we cancelled small r is 4 plus x equals to, there's a mistake here, so capital R equals to 9 plus r minus x according to our first equation. So I will do it again. R equals to r, that is to say capital R according to our first equation equals to 9 plus r minus x. That is the value of capital R according to our first equation, and it equals to capital R as we calculated it in our second equation, that is to say it equals to 4 plus r plus x. Okay, again, here is capital R as we calculated it in the first equation, and here is the value of capital R as we calculated it in the second equation. So capital R equals to capital R. So here we have R in this side of the equation, and we have R in the other side of the equation, so R is cancelled. So what is left after we cancelled R is nine minus x equals to 4 plus x. Here we will subtract 4 from this third equation, and we will get that 9 minus 4 is 5 minus x equals to x. Okay, 5 minus x equals to x. Here we will add x from this equation, and we will get that 5 minus x plus x is 5, and x plus x is 2x. So here we will divide equation number 3 by 2 in order to get the value of x. So x will be equal to 5 over 2, that is actually 2.5 units, okay? So we got the value of x equals to 2.5 units. Okay, so now we will return to equation number 1. According to equation number 1, capital R equals to 9 plus small r minus x. That is actually equation number 1. According to equation number 1, capital R equals to 9 plus r minus x, but we have already found out that the value of x is 2.5 units. So we can substitute x by 2.5 units, and we will get that capital R equals to 2 minus 2.5 plus R. Okay, capital R equals to 2 minus 2.5 plus R. 2 minus capital R equals to 9 minus 2.5 plus R. 9 minus 2.5 is 6.5. So in total we got that capital R equals to 9 capital R equals to 6.5, because 9 minus 2.5 is 6.5 plus small r. Okay, so I will write it down. So according to equation number 1, capital R equals to 6.5 plus small r, and we also know that x equals to 2.5 units. Okay, according to equation number 1, we got that capital R equals to 6.5 plus small r, and we have already found out that x equals to 2.5 units. Okay, in the next step we will present a rule number 1, and then we will implement rule number 1 in our two circles. Rule number 1 states that if two circles have internal length between them, if two circles have internal length between them, then the distance between their centers, the distance between their centers is equal to the difference between the lengths of their radiuses. Okay, so I will read rule number 1 again. Rule number 1 states that if two circles have internal length between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. Okay? So actually we can implement rule number 1 in our two circles, because we have those two circles have internal length between them at point N. So we can use rule number 1 here. According to rule number 1, the distance between their centers, that is to say, the distance between Q and P is QP, because Q is the center of the small circle and P is the center of the big circle. So the distance between the centers of those two circles is QP. Okay, the distance between Q and P is the distance between the centers of those circles, QP. Okay, so I will write it down, that QP equals, according to rule number 1, QP equals to the difference between the length of their radiuses. The difference between the lengths of their radiuses is capital R minus small r. So actually we implemented rule number 1 in our two circles, because our two circles have internal length between them. They have internal length between them at point N. They are touching each other at point N from inside. therefore we can implement rule number 1 that states that in this situation the distance between their centers, that is to say QP, equals to the difference between the length of their radiuses, that is actually capital R minus small r, or QP equals to capital R minus small r. Okay, so from this we can add small r for this fourth equation, and we will get that capital R equals, after we added small r to the fourth equation, we will get that capital R equals to QP plus R. Capital R minus R plus R is capital R, and QP plus R is QP plus R, or QP plus small r. So we have this fourth equation that states that the radius of the big circle equals to QP plus small r, but we have already found out in the first equation that the value of capital R is actually 6.5 plus small r. Okay, we have two expressions for capital R, so we can again compare equation number 1 to equation number 4. We can write down that capital R equals to capital R. This will be equation number 5. And here we'll substitute capital R by the value of capital R according to equation number 4. And we will substitute this R by the value of capital R from equation number 1. And we will get that equation number 5, the following equality that states that QP plus R equals to 6.5 plus small r. Okay, so we got this equality that QP plus R equals to 6.5 plus QP plus small r equals to 6.5 plus small r. Here we have small r in this side of the equation, and we have small r in the other side of the equation, so we can cancel r. Okay, and we got the value of QP according to equation number 5. QP equals to 6.5 units. Okay, so we got the value of QP. QP equals to 6.5 units, and we have already know, according to equation number 3, that X equals to 2.5 units. Okay, so in the next step we will connect together points Q and P by a straight line. And actually we have here a right triangle. The triangle in the green color is a right triangle because of the fact that this angle QMP, is a right angle. For that reason, triangle QMP is a right triangle. So I write it down that triangle QMP is a right triangle. So therefore we can implement the Pythagorean theorem in the right triangle QMP. Okay, so according to the Pythagorean theorem, so I read again the things that I wrote. Triangle QMP is a right triangle, so according to the Pythagorean theorem, the Pythagorean theorem states that in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, QP square equals to PM square plus QM square. Again, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, so QP square equals to PM square plus MQ square. Okay, so write it down. QP square equals to PM square plus QM square. Okay, so according to the Pythagorean theorem, the square of the hypotenuse, that is to say QP square, equals to the sum of the squares of the perpendiculars equals to PM square plus QM square. But we have already found out that QP equals to 6.5 units, so QP square will be equal to 6.5 square. That equals to PM square. PM equals to X, so X, PM square is X square plus QM square. QM equals to small r, so QM square is r square. Okay, so we got this equality that states that 6.5 square equals to X square plus small r square. But we have already found out that the value of X is 2.5 units, so we can substitute X by 2.5 units, and we will get that 6.5 square is actually 42.25 equals to 2.5 square. 2.5 square is 6.25 plus r square. So we got this equality that states that 42.25 equals to 6.25 plus r square. Here we'll subtract 6.25 from this equality, and we will get that 42.25 minus 6.25 is 36 equals to r square. Okay, we got that 36 equals to r square. In the next step, we will take a root out of this equality, and we will get that r equals to the root of 36. The root of 36 is 6 units. So we found out the value of the radius of the small circle, or the size of the radius of the small circle is actually 6 units. Okay, so that is the answer to the question that the size of the radius of the small circle is actually 6 units. Okay, so now I will summarize the lecture. We actually wanted to find out the radius of the small circle. We have here two circles that have internal lunge between them at point N. The two circles are touching each other at point N from inside the big circle. The small circle touches the big circle at point N, and we also know that AB is the diameter of the big circle. We know that AC equals to 9 units, DB equals to 4 units, and we know that this is a right angle and also this is a right angle, and we have also 3 tangents to the small circle, and we want to find out the radius of the small circle. Okay, first of all we defined as the radius of the small circle as R, and we defined the radius of the big circle as capital R, and then we will also define the point Q as the center of the small circle, and we defined point P as the center of the big circle. Okay, as I have already mentioned, AB is the diameter of the big circle, and we have 3 tangents to the small circle. This is the first tangent to the small circle. This line segment is tangent to the circle at point S. Line segment CD is tangent to the small circle at point M, and this line segment is tangent to the circle at point Z. Okay, so we actually built 3 radiuses of the small circle from the center of the circle, that is to say from point Q to the points of contacts between the tangents to this circle to the circle. So the first radius of the small circle is QS, and S is the point of contact of this line segment with the circle. So this line segment is tangent to the circle at point S, and R is actually the radius that touches the tangent to this circle at point S. Therefore, when you have a radius, any radius is perpendicular to its tangent, and this is the tangent to the radius and to the circle. Therefore, the radius is perpendicular to its tangent, that is to say this angle is a right angle. Okay, and then we have also we draw the second radius of the small circle that exits from point Q and ends at point Z, and point Z is actually the line segment. This line segment is tangent to the circle at point Z. It is actually also tangent to the radius at point Z. So we have the rule that states that the radius is perpendicular to its tangent. That is to say, this is also a right angle. Because of the fact that the radius is perpendicular to its tangent, and this is the tangent to this circle at point Z, that is to say, this angle is a right angle, because of the fact that the radius is perpendicular to its tangent. Okay, and then we drew the third radius from point Q to point M, and again point M is the point of contact between line segment CD to the circle, or line segment CD is tangent to the circle at point M. Okay, so line segment CD is tangent to the circle and is also tangent to the radius QM. So we know that the radius is perpendicular to its tangent. So the radius is perpendicular to CD, that is the tangent to the circle and also tangent to the radius. Therefore, this is a right angle and also this is a right angle. Okay? Then we actually created square QZMD. We have square QZMD with 3 right angles. This is a right angle, this is a right angle, and also this is a right angle. And we know that the sum of the angles in any square equals to 360 degrees. Therefore, the fourth angle must be equal to 90 degrees, because the value of the fourth angle is 360 degrees minus 270 degrees. That is the sum of the 3 right angles. Therefore, this angle is also a right angle. So here we have a square with 4 right angles, and any square that has 4 right angles is a triangle. So QZMD is a triangle, and in any triangle the opposite sides are equal to each other. So QZ is equal to MD, and we know that QZ equals to small r. Therefore, MD that equals to QZ also will be equal to small r. Okay? And then we have here, we repeated the same process on shape SQCM, that is actually a square. In this square we have 3 right angles. So the fourth angle must be also a right angle, because the sum of the angles in any square equals to 360 degrees. Therefore, we have here a rectangle, because any square that has 3 right angles is a rectangle. So SQCM is a rectangle. Therefore, SQ equals to CM, because there are 2 opposite sides, and the opposite sides in a rectangle are equal to each other. And if SQ equals to R, then CM that also equals to SQ will be also equals to R. Okay, so we proved that CM equals to small r, and MD also equals to small r. Okay, then we defined PM as X, and the value of CP is actually CM minus PM. CM minus PM is CP. and cm equals to small r, and pm equals to x according to our definition. So the value of cp is actually cm, that is r, minus pm, that is x. So cp equals to r minus x. Okay, then we calculated the size of the radius of the big circle in two ways. From one side, the radius of the big circle equals to AP. So AP equals to capital R, and so AP equals to AC plus CP. That is to say, AP that equals to capital R equals to AC, that is 9 units, plus CP, that is R minus X, or the radius of the circle equals to AP plus CP. In other words, the radius of the circle equals to 9 plus R minus X. Okay, so from one side we found that the radius of this circle equals to 9 minus small r minus x, but we can calculate the radius of this circle in the second way. The radius of the circle also equals to PB because of the fact that AB is the diameter of the circle. AB equals to 2 times the radius of the circle. The diameter equals to 2 times the radius of the circle, so PB is also the radius of the big circle, and PB equals to small r. And what is the value of PB? PB actually equals to BD plus MD plus MP. Okay, PB equals to BD plus MD plus MP, but we know that BD equals to 4 units, MD equals to the radius of the circle, and MP equals to x. So R equals to 4 plus small r plus x. Again, BD equals to 4 units, MD is the radius of the small circle, and PM equals to small x according to our definition. So capital R equals to 4 plus small r plus x. That is the second way of calculation of the radius of the big circle. We have the first way, that the radius of the circle equals to 9 plus r minus x. That is the first way that we calculated the radius of the big circle. And in the second equation we have the second way of calculation of the radius of the big circle. So we can compare equation number 1 to equation number 2, because it is the calculation of the big circle, the radius of the big circle, in two different ways. So we can state in equation number 3, we can say that capital R equals to capital R, and then we will substitute capital R from equation number 1 by equation number 1, and here we substituted capital R by equation number 2. Okay, so we actually compared equation number 1 to equation number 2, because both of these equations are the expression of the radius of the big circle in two different ways. So they are equal to each other. Capital R equals to capital R. Okay, and in this way we got equation number 3. And from equation number 3 we found out that the value of x equals to 2.5 units. Okay, so according to equation number 1, the radius of the big circle equals to 9 minus 2.5 plus r, or the radius of the big circle, after we know the value of x, equals to 2.5 to 2. X equals to 6.5 plus small r, or capital R equals to 6.5 plus small r, and the value of x is 2.5 units. Okay, and then we presented a new rule number 1, and we implemented rule number 1 in our circles. According to rule number 1, if two circles have internal length between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. Okay, so we actually can implement rule number 1 in our circles, because we have two circles that have internal length between them at point N. Therefore, we can use rule number 1 that states that the distance between their centers, that is to say QP, because Q is the center of the small circle and P is the center of the big center of the big circle, the distance between those two, the centers of those two circles, is QP, and QP equals to, according to rule number 1, QP equals to the difference between the lengths of the radiuses, that is to say QP equals to capital R minus small r. Okay, so according to equation number 4, capital R equals to QP plus R, and we have equation number 1 that states that capital R equals to 6.5 plus small r. Again, we can compare equation number 4 to equation number 1, because both of them are the expressions of the same radius. So we can say that capital R equals to capital R, and then we substitute capital R by equation number 4, and in the other side of the equation we substituted capital R by equation number 3, and we got that the value of QP is 6.5 units, and we have already found out that the value of x equals to 2.5 units. Okay, then we connected points Q and P by a straight line, and we got the green triangle. The green triangle QMP is a right triangle because of the fact that angle QMP equals to 90 degrees. So we can use the Pythagorean theorem in order to find out the value of QM, that is the radius of the small circle, because we know that QP equals to 6.5 units and PM that equals to X equals to 2.5 units, and the only missing variable is the radius of this circle. So we found out the radius of this circle according to Pythagorean theorem that states that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, QP square equals to PM square plus QM square. Again, we have all the data, all the values of this equality, and the only missing variable is the radius of the circle. We put the data inside this equality, and we found out that the radius of the small circle equals to 6 units. Again, the radius of the small circle equals to 6 units. Okay, thank you very much.